we're going to work on implicit differentiation. This is going to be differentiation when you can't easily solve for one of the variables that you want to work with. In this one, we can kind of solve for y if we wanted to. I'd move things around like this. I'd find 6x squared minus 8 equals y squared. And, well, maybe I want to get y by itself. So what would get y by itself? Square root. 6x squared minus 8 equals y, except I need a plus or minus here. Okay. Now if I wanted to, I could differentiate this. Might be helpful if I regard that as 6x squared minus 8 to the 1/2 power. And then I can find its derivative. I'm just going to move it over here, dy by dx. What's going to happen when you differentiate this? What rule becomes your friend when you try and find the derivative here? Chain rule, yes, thank you, chain rule. So it's going to be plus or minus 1/2 times 6x squared minus 8 to the negative 1/2, because that negative comes from 1/2 minus 1, so negative 1/2. But we're not quite done there, are we? What else do we got to do? Yeah, well done. In chorus, too. Nice. Times derivative of the inside. Derivative of the inside is 12x. The 2 and the 12 can cancel each other out. That's going to leave me with a 6x. That 6x is going to be in the numerator. This term is going to be in the denominator. So I'll write plus or minus 6x over, well, you could write it as 6x squared minus 8 to the 1/2 power, or you could replace that with a square root. Either one is okay. Either one is fine. I don't have much preference for one versus the other. That's doing things explicitly. You're able to solve for y and then move on. But we can't always solve for y. And if you can't solve for y, then you've got to do something else called implicit differentiation. Now, implicit differentiation is going to be part of our work with related rates problems and some other things in this course. So it's not something that's going to go away. Let's see if we can't try and conquer it here. This was explicit. We were able to actually find this. So explicit. Let's take a look at the difference between that and implicit. And even though we might have solved for y, there is still some kind of a relationship between x and y. And so we can differentiate things that way. Let's take a look at how that's going to be. Now, the one thing I suggest when we start differentiating with respect to this, or differentiating these things implicitly, is this. Wherever there's a y, you want to write yourself a little something around that y. Like, let's take and write it in blue here like this. Because when you differentiate, you're going to get some kind of a application of the chain rule. You're going to have to do the derivative of the outside times the derivative of the inside. So let me rewrite that like this. 6x squared minus y squared equals 8. Let's put that here. I want to differentiate this with respect to x. So if I'm going to take the derivative, do you remember what my notation was? What have I always been writing for that? You're going to take the derivative. d over dx. So I don't have a y here. It means I'm going to take the derivative. Now the derivative of this part is pretty easy, right? It's just 12x. But when you differentiate this one, it's not just 2y. 2y is the derivative of the outside. So 2 times y, and that's going to be to the first power. But then we got to multiply by the derivative of the inside. And the derivative of the inside is your dy by dx. You just can't simplify it. It doesn't go any further. How about the derivative on the right-hand side? 0. So that derivative of the inside term is not going away. But we can solve for that. That's what we want to get by itself. We want to get dy by dx by itself. So let me do it this way. I'm going to move the 12x to the other side. That gives me negative 2y dy by dx equals negative 12x. Almost done. What do I have to do to simplify? To get dy by dx by itself? Yeah, divide by negative 2y. So I get negative 12x over negative 2y. Or in other words, I get 6x over y. Now that looks like a much different expression than the dy by dx I got over there, doesn't it? It's like, yeah, that doesn't look anything the same. But if you wanted the slope of the tangent line, you could get it from here or here. The difference with getting it here is that I only need to know the x-coordinate. Here I need to know the x-coordinate and the y-coordinate. And because there's a lot of skeptical looks on your faces here, let me clean this up just one more step. What if I wanted to replace something for y? I could do that because I solved for y over here, didn't I? Y is plus or minus the square root of 6x squared minus 8, or better yet, let's just use the parentheses there. So if I replaced y with that square root, it'd be plus or minus 6x squared minus 8 to the 1/2 power. And somebody said it for me right up here. It's the same, right? So you're getting the same thing. You're still getting the derivative. It almost feels like hocus pocus the second time we did it. It's like that just felt weird. And you're right. It's much different than what we've been doing. No ifs, ands, or buts. But it's what you're going to have to do sometimes if you can't explicitly solve for a variable. In this first one, we were lucky. We were actually able to solve for y. But if you can't, then you're going to have to do something like this. So Arlie gives a grudging kind of like, okay, if you insist. All right. Any comments on that one? Let's take a look at example B here, our so-called Fulham of Descartes. So this is an example of a place where you can't really solve for y. This part of the Fulham, is just not a function. We don't have y depending explicitly on x. But we still want to try and find, actually is that the Fulham? Yeah, I think this one's the Fulham. We actually do try and want to find some of the derivatives here. No, that's example D, that's the Fulham of Descartes. We're going to work with example B next. And let's see what goes on there. Example B. So you've got x squared minus 14xy plus y squared equals 14. You guys are going to really have fun with this section. I envy you in doing the homework. Before we get started here, there's a couple things I want to do. The first thing I want to do is play around with the terms in y. Everywhere there's a y, you don't have to do this, but I recommend it because it's drawing your attention to the fact that when I differentiate with respect to y, I have to use the chain rule. So, okay, there's our function. I want to take the derivative of both sides, so d by dx. I want to differentiate both sides of that. Let's start with the easy parts. Derivative of 2x, or excuse me, whoops, derivative of x squared, 2x. Thanks, Alex. So 2x. Let's also do the derivative on the right-hand side. 0. Nice. But take a look at what we got in the middle. Let's start with this one. Derivative of y squared. 2y, so that's going to be derivative of the outside. 2 times y. So there's your derivative of the outside. Times the derivative of the inside. What's the derivative of the inside? dy by dx. It'd be 1 if I was differentiating with respect to y, but I'm not differentiating with respect to x. And this middle term, this one's kind of a pain. What rule am I going to have to use to differentiate x times y? The product rule, you're right. So let me squeeze this in here. It's going to be minus 14. And then it's the derivative of the first times the second plus the derivative of the second times the first. Help me out with the derivative of the first. Derivative of x is 1 times y. Yeah, just y. Yes. Nice. And then the derivative of the second times the first. So plus, yeah, dy by dx times x. I'm sorry, I'm squeezing that in there a little bit. Should have given myself a little bit more room. Let me distribute that 14. I'm also going to put in here, just for your notes, we want to use the product rule. So you got to use the product rule on that part. Let's distribute the negative 14. That's going to be 2x minus 14y minus 14 times the x here, 14x times dy by dx, plus 2y, and that's to the first power, so I don't need to just write that anymore. I'll just get rid of that, equals 0. So that's my derivative. But then I need to solve for dy by dx. If you notice, a couple of these terms don't involve the derivative, don't involve the dy by dx. These terms I want to keep here. These other terms, I'm going to get rid of them. So that one I'm going to move to the other side. That one I'm going to move to the other side. When something changes signs, it also changes signs. Gosh, I'm messing that up here this morning. If it changes size, it changes signs. So that's going to leave me with a 14y minus a 2x. And on the left-hand side, let's do this. And I apologize that I'm doing a lot in one step here. If I factored out the dy by dx, that's going to leave behind a minus 14x plus 2y. Okay. Almost done. I want to get dy by itself, but dy is being multiplied by this. What's the opposite of multiplication? God, I can't talk all of a sudden. Divide. Dy by dx equals 14y minus 2x over negative 14x plus 2y. And that's your derivative. You could clean up a factor of 2. If I wanted to clean this up, I divide out the 2. That's going to leave behind 7y minus x over, let's take out the 2 from here and write it as y minus 7x. And that's about as far as you can go with it. I don't know if I'm going to mark you wrong if you don't take out the 2. I think I'll be pretty happy you getting here, but it's not a bad idea to clean things up. Whew. A lot going on with that one. Let me pause, look back at this. If you have some spots where maybe I went a little too fast, let me know. So we started by recognizing that, yeah, we can't get y by itself, so the best thing we'll do is use the chain rule and differentiate implicitly. That means whenever you differentiate this term in y, you've got to have a dy by dx term for it. So derivative of the outside times derivative of the inside, we got the dy by dx. Using the product rule here, I got a dy by dx when I differentiated that. Distribute, solve for dy by dx. Okay. Let's take a look at example C. So y times cosine of x equals 3x squared plus 4y squared. I'm going to start as usual by just putting these y's in brackets like this, just to call your attention to the fact that those need special care when we differentiate both sides with respect to x. Lucas, on the left-hand side, when I differentiate this, in addition to the chain rule, what else am I going to need to use?
Power rule.
Not the power rule. It starts with a P, though.
A product.
There you go, product rule. So derivative of the first times the second plus derivative of the second times the first. Cool. And on the right-hand side, we're also going to need differentiate with respect to y, or excuse me, with respect to x by using the chain rule here. Keegan, maybe you can help me out here. When I differentiate with the product rule, what's that going to give me? First term. So this would be your f, that'd be your g. I want f prime g plus g prime f. Nice. dy by dx times g, which is your cosine of x. Keep going.
Plus negative sine x times y.
Perfect. That's our right-hand side. Let me illustrate something with 3x squared. Because some of you might be a little confused, well, how come we don't get that crazy stuff when we differentiate the 3x squared? Suppose I write this as 3x squared, and I said, well, we're going to differentiate with respect to x here. I'm going to take d by dx. Let's just move this out of the way for a second. Okay, the 3 you're going to ignore, and then the derivative of the outside is going to be the 2, and then this to the first power, times the derivative of the inside. But the derivative of the inside is going to be dx by dx, right? Notice that these things are the same. What is dx over dx going to give me? 1. So you just get 6x times 1, or better yet, 6x. So if these variables match, that's great. You don't have to worry about things like we do when we have the y's. If you've got a y, you're going to get dy by dx. Those two variables won't match. You're not going to get rid of that term. Let's keep going here. That's just going to be our 6x plus 4 times the 2 times y to the first power times the derivative of the inside. What's the derivative of the inside going to be? dy by dx. So let me clean this up a little bit. That's going to be cosine of x dy by dx minus y times sine of x equals 6x plus 8y dy by dx. You've got dy by dx on both sides. You have to decide what side you want to put your dy by dx's on. The left-hand side or the right-hand side. Your choice. There's no perfect answer. Left-hand side? All right, left-hand side. So that means I'm going to move that term to the left-hand side. Since this one doesn't involve a dy by dx, I'm going to move it to the right-hand side. And we're going to get some sign changes. So you're going to get cosine of x dy by dx minus 8y dy by dx equals 6x plus y sine of x. Yep, factor out. So it's going to leave me with cosine of x minus 8y times dy by dx equals 6x plus y sine of x. If I divide both sides by this coefficient, I end up with dy by dx equals 6x plus y sine of x over cosine of x minus 8y. Whew! Grab the oxygen bottle. All right. So same kind of thing all the way through. Let me just take a look. I'd like to do that one last one with the full limb of Descartes. You know what? I don't know. I think we worked hard enough today. We can do that next time.